In this lesson, we're going to carry on with financial applications. This is the third lesson on financial applications, and this time we're going to look at something called an annuity. An annuity is if you make regular payments let's call it payments. Regular payments into they call it a savings account. How much are we going to have at the end? That would be future value. In another lesson, we're going to look at something called present value, which is basically where we're taking regular withdrawals from a sum of money. How long would it last for? How much could you take out? Anyway, I'll get into all the details shortly, but that's the idea of regular payments is what's going to matter. So let's just do an example to start making it a little clearer. Christine decides to invest $1,000 at the end of each year. And it matters whether it's the beginning or the end, so we're doing the end. That's going to be common to do at the end of a time period. In a Canada Savings bond that earns 6.5% per year, compounded annually, just to keep things simple, how much will her investment be worth 5 years later? Okay, so this is a timeline that you can see here. It lays out the year, like how much time has gone past. So today, right now, let's pretend it's right now, or let's not say it's right now. Let's say it's the end of a year, or January 1st, okay, or December 31st, whatever. So December 31st this year is time 0. 1 would be 1 year later, so December 31st next year. And then 2 would be December 31st 2 years later, and so on. So that's what those numbers across the top are at the time. And then there's the investment, right? How much is being invested and when. So December 31st this year, nothing. But 1 year from now, she's going to put $1,000 in. And 2 years from now, she'll put another $1,000 in. And then another, and then another. And then she'll put another $1,000 in 5 years from now. And she wants to know how much her investment is worth at that time. Well, hopefully it'll be worth at least $5,000 because she's put 5 times $1,000 in. But it should be worth more than $5,000 because each of these $1,000 will be earning interest. Now, if we consider them as 5 separate investments, then we can work out what each one is individually. So the $1,000 she invests at the end won't have earned any money. Because she's putting it in December 31st, 5 years from today, or 5 years from the end of this year, and then she's also seeing how much her investment is worth at that same time. Well, in that case, it'll be $1,000, right? She puts $1,000 in and then checks the balance. Still $1,000. So that makes sense. But what about the one that she invests 4 years from now? So 4 years from now, she invests $1,000, and then it'll have had 1 year to sit in the bank to gain interest, right? So she invests it now, or at 4, and then at 5, she checks how much it's worth. So 1 year has gone past between these two dates. Well, that $1,000 is going to earn 1.065 because that's my I value, right? It's compounded annually, so it's only once a year in this example. So we do 1.065, as we know from our compound interest formula. Let me remind you what that is. A equals P times 1 plus I to the N. So 1 plus 0.065, and N is the number of years that have gone by. It's the number of compounding periods, but it's once a year, so it'll be 1 in this case. And then what else? Well, if we go backwards to the next one, at the $1,000 she invested at 3 years at year 3, will have had 2 years to grow, won't it? It's growing from year 3, and then at year 5 we're calculating what it's worth. So 2 years will have gone past. So what we really have for this $1,000 here is an investment of 1,000 times 1.065 to the exponent 2. The only thing that's changing is the exponent 2 here. And so you can start to see a pattern forming, right? The next one back would have 3 years to grow. And so it's going to be $1,000 times 1.065 to the exponent 3. And then the next one's going to be $1,000. This one here will have 4 years to grow. And so that would be $1,000 times 1.065 to the exponent 4. We could even, if I wanted to backtrack and use the formula, say this first one is $1,000 times 1.065 to the exponent 0, right? And we know that anything to the exponent 0 equals 1, so what I just highlighted in green will simplify down to 1, so that still gives us our $1,000. So the future value, so in other words, if we were to add all this up to find out how much money she has, she'll have different amounts for each one. This $1,000 investment's worth $1,000. This one's worth, I guess, $1,065 because she'll have got $65 interest for that 1 year. This one will be worth $1,140, somewhere around that, a little bit more. And then this one will be worth more still because every one that's got a higher exponent, getting down to this one with the exponent 4, has had more time to earn interest. So they're all different amounts. If we add each of these 5 mini investments together, then we know how much Christine's final value is going to be. So it's going to be 1,000 plus, I'm just going to write it out without calculating it, plus 1.065 to the exponent 1, plus 1,000 times 1.065 to the exponent 2, and so on. Well, this should look kind of familiar. It's been a little bit since we've done sequences and series, but really this is a series. Remember what a series is? It's where you have a bunch of terms, but you're adding them together, and that's exactly what we're doing here. We're adding all these terms together. And to be more precise, it's a geometric series because it's going up by a common ratio. The common ratio is the 1.065. So another way I could think about it is if I took this number and I multiply it by 1.065, then I get the second term. And if I took the second term and multiply the one I've got circled in red by 1.065, I get the next term. And then if I multiply by 1.065, I get the next term, and so on. So every one of these terms I get the next term by multiplying by 1.065. That's what increasing the exponent by 1 each time does. So it's a geometric series. And then we can use this formula, if you remember the formula for a geometric series. S for series of n, so n terms, is equal to A, the initial amount, times r to the n. R is the common ratio, and n is the number of terms. So minus 1 and then over r minus 1. So those are the values we need to know. We need to know A, R, and N. So in this particular example, we're still carrying on with example 1. The initial amount is $1,000 each time. R is 1.065. That's our common ratio from above. And N is 5. There's 5 terms. So if I want to work out the sum of this series, I could do S sub 5, so the 5 investments, is equal to 1,000 times 1.065 to the exponent 5 minus 1 divided by 1.065 minus 1. So it's just going to end up being the 0.65. And that should give us the sum of the series. 1,000 times 1.065 exponent 5 minus 1 divided by, I'll actually type it in the way it's supposed to be, 1.065 minus 1. Obviously, again, that denominator is just going to simplify down to 0.065. But anyway, I get $5,693, and I'll get the cents in a second. $5,693.64. Remember, initially I said that our investment should be worth, something over $5,000. We better have at least $5,000, otherwise it's a bad investment. We put $5,000 in, and then the $693 and 64 cents is interest. Now, just to prove that this is true, let's go back and just work out what these are. So 1,000 is 1,000, obviously, and 1,000 times 1.065 would be 1,065. And 1,000 times 0.65, oops, too many zeros, times 1.065 squared is 1,034.23. And then if I cube it for the next term, just change this exponent to a 3, it's $1,207. That seems like a lot. Felt like a big jump there. Did I miss something? Let me just go back for a second. I feel like something's wrong. No, it should have been 1,134 for squaring it. Oh, I see. 1,001. Okay. Pardon me while I talk to myself. I knew that something looked wrong. It should have been a 1,134. All right, so the next one, if I change the exponent to a 3, becomes $1,207.95. And then the last one, if I change the exponent to a 4, becomes $1,286.47. So if I take all of these and add them together, 1,000 plus 1,065 plus 1,134.23 plus 1,207.95 plus 1,286.47. I got $5,693 and 58 cents. So compare that to this. Identical? No. Similar? Yes. The difference is in the rounding, because of the fact that I've been rounding in this one here. It's not quite right. So they're close, but this one would actually be correct. So this formula that actually does it in an easier way, doing it all at once, is the correct answer. And that's what goes in this spot here. $5,693.64 is what the investment's worth. So we can use the geometric series formula to do this, to find out what something's worth in the future under certain conditions. And again, the conditions are this. It has to be a regular payment. So in other words, 1,000, 1,000, 1,000, 1,000, 1,000, same amount each time. And regular also means regular time period. So 1 year, 1 year, 1 year between each one of them. So it's the exact same time period in between each one of them. It also needs to be at the end of the time period. That's important. It doesn't always have to be that way, but for this formula to work, it does. So we're going to stick with ones that are always at the end of the time period when they're submitted. So this formula here, the geometric series formula, can be rewritten as the formula for the future value of an annuity. So in other words, all that this box that I'm highlighting in red or putting a red box around The only difference between it and the geometric series formula is that it's just got different variables to match the financial nature of the application. So instead of saying the sum of the series, we talk about FV for the future value. Instead of talking about A as our initial amount, we talk about R. R stands for regular payment. And instead of talking about little r and n, well, we still talk about n, but instead of little r, we talk about I as our interest rate per compounding period. So just going back to what we had for compound interest, n is still the total number of compounding periods. And so we've got these, just some different variables. Look at the bottom where it just says I. Remember, r minus 1 up here. Remember, r was just 1 plus I, so 1 plus I minus 1 is just I. So really it's just simplifying down to the same thing that we would get anyway. So this formula here is what we want to use. Again, it's the same as the geometric series formula, but it's fitted for financial applications. So let's use it. $100 is deposited at the end of each month for 5 years at 6% compounded monthly, okay? 6% per annum, compounded monthly, 5 years, $100, end of the month. Find the amount on the date of the last payment. So this is just straightforward using the formula exactly as it was intended. So identifying different things, my regular payment is $100. I calculate the same way as I do for compounded interest and present value. I take my annual amount and divide it by the number of periods per year. So monthly is 12 per year. So that becomes 0.005. N is where I take the number of years and multiply it by the number of periods per year. So 5 times 12 means 60. It just means if for 5 years, if I invest $100 a month for 5 years, I'm going to invest $100 60 times. And that's all I need. Those are the only things I need to get the future value. Using the formula, R is 100, 1 plus I is 1.005, N is 60, then I subtract 1, and I put it over I, which is 0.005. Type that in, and I'll have my answer immediately. Bracket 1.005 to the exponent 60 in this case. Minus 1, end bracket, divided by 0.005. $6,977 and 0 cents if I round to 2 decimal places. Last thing I would do is just check, does this make sense? So if I invest $100 a month for 60 months, then I've put $6,000 in. The final amount is $6,977. 6% interest rate is pretty good. It's for 5 years, which is, sort of medium length of time. I could see that it's possible that it's earned $977 in interest. So I'd say, yeah. Logic tells me that this is not an outrageous answer. It makes sense to my just paying attention to it. Here's another example. We're just going to change things around a little bit. We're going to take the formula and just solve for a different thing. We're going to solve for R. Nick wants to invest money every week for the next 5 years. He'd like to have $20,000 at the end of this time. So, in other words, he's thinking ahead. Maybe he wants to go to university. Maybe he wants to buy a car. Who knows? But he knows he would like to have $20,000 at the end of 5 years. So, he can find an investment of 3% a year compounded weekly. So, weekly is implies 52 times a year. How much does he need to invest each week? So in this case, we're asking how much is he going to need to put in every week in order to do this? So you can probably hear my dog going crazy in the background. Someone's just come to the door. All right, so in this case, it's going to be useful to rearrange the formula in order to isolate R. So if we start with FV equals R times 1 plus I to the exponent n, and I want to get R by itself, we'll just solve this like an equation. So I'm going to multiply both sides by I for starters. So FV times I gets it out of the bottom. And I've got R times 1 plus I to the n minus 1. And then, again, just to get R by itself, I could take this entire bracket and just divide both sides by it. It'll get rid of it on the right-hand side, and what I'm left with is FV times I over 1 plus I to the n minus 1. And now I've got R by itself. So this is a good formula. I'm just going to rewrite it with R on the left-hand side. So R equals FV times I over 1 plus I to the n minus 1. So this, I would say, just keep this formula handy anytime you are asked to find out what the regular payment is in a future value annuity situation. So I still need to know various things. So the $20,000 in this original question is the future value. It's what I want it to be worth. I is going to be 3%, not just 1 0 in front of it, divided by, remember it was weekly up here, so divided by 52. So that's going to be probably a bit of a longer decimal. Let's see what it is. So in scientific notation, that times 10 to the 4 just means I can move the decimal place 4 to the left. So it would be 0.000576. What else? Maybe I'll just go one more decimal place, put the 9 there. I just like to have a lot of decimal places on my interest rate because a small change in interest can make a big difference in my answer. So I've got 7 decimal places there, which should be plenty, but I like to do overkill when I'm doing my interest, when I'm calculating my interest rate per compounding period. And I need to know n again. So it was 3 years weekly. So again, I'll take the 3 years, multiply it by the 52 of weekly. That equals 156. So again, once I've got the formula I'm using, once I know what goes in for the variables, then it's pretty easy calculation. So R is going to equal future value $20,000 times I, which was 0.0005769 over 1.0005769 to the exponent 156 minus 1. So I just have to be careful to maintain order of operations when I actually type this in. So 20,000 times 0.0005769, that's my numerator. Divide that by, I'm going to use brackets to make sure that my denominator gets done all before I, so that maintain order of operations. So 1.00579, same number, except that with the 1 in front, to the exponent 156 minus 1 end bracket. That 20,000 out front, I could put it up top. It doesn't matter that much, as long as the main thing is that I have to do my denominator. I have to do the exponent minus 1 before I divide. And I got $7.94. That seems a little low. So I may have made a mistake. So I'll write it down first, and then I'll double check. So let's just do a quick. So something doesn't ring quite true. And I may have been distracted by my dog going crazy a few minutes ago, but let's just check it out. So a quick check I could do is 794 times the 152 is $1,206. So that would mean I put in $1,206 and it would have grown to $20,000 in 3 years. Something doesn't ring quite true. Unfortunately, I cleared my calculator. I should have kept it. But I wonder if maybe I didn't put quite enough zeros down. So let's try again. 20, 1, 2, 3, times the interest rate, which was, or it's also possible I didn't put enough decimals down, 0, 0. I think maybe I might have only put 2 zeros is the other thing. So somewhere in there I made a mistake. But I'm paying attention and trying to backtrack and work it out. It also doesn't help that I'm talking while I do it, sort of dividing my attention between teaching and working. Let's see what happens if I type it in again. Now this time I get $122.56. That seems a lot more reasonable. 122.56. So I feel comfortable with this one, but let's check it. Okay, let's take the answer, multiply it by 156, see what it equals. $19,119. Okay, that's very close to $20,000. It's just a little bit under, but that sort of meshes with what I would expect. The interest rate they're getting is, remember, only 3% per year. That's not huge, not terrible in today's market, but it's not going to make things grow that much. And it's also, 5 years is like I said, a moderate amount of time, but when you put it together with the interest rate, it'll have earned what? About almost $1,000 in that time, $900. It's not terrible, but at least it's reasonable. And so I feel a lot more comfortable with that solution. So I think that I just got distracted on the first time through, but I'd like to take that as a teachable moment. If you check your answers, then you'll still be okay.